read the manual that I shared just now. So basically, today we're going to do another experiments in terms of to learn about the kinetic theory of the gases. So during the lecture, so you have learned about the theory of the kinetic for the motion. Alright, so today in the lab session, we're going to learn the theory of the kinetic theory on the gas. Right, but this will also be covered later in the lecture. Alright, so to start, so let's open our lab manual. Give me a while. I can see my window over here. Oh. All right, so okay, so we are now on the experiment 2. So for the learning outcome for today, we're going to record a repetitive data set from online experiment to perform investigation on Boyle's law and also Charles' law and also Gay-Lussec's law. All right. So all of these laws are related to the kinetic theory of the gases. Okay, and then next we're going to also, all right, so the last one we're going to also record the kinetic theory of the ideal gas, so based on ideal gas, and the kinetic theory, all right, kinetic energy of the gas at different temperature, pressure, and volume. And also, we're going to calculate the mean of the recorded observation and find the standard deviation of the set and analyze the results and relate the results to Boyle's law, Charles' law, Gay-Lussec law, and the kinetic theory of ideal gases. So basically, today's experiment will be a straightforward one. So, because you already have enough exercises given for the first lab, which you learned extensively on how to perform the error analysis. So this one should be a straightforward experiment for you. Okay, so let's go to the introduction. So the aim of the kinetic theory is to account the properties of gases in terms of the forces between molecules. So we assume that the motions are described by the law of mechanics, right? So we use Newtonian mechanics, right? And also the quantum mechanics. So here we use the Newton's second law of motion, okay? But it is stated in not so family form as impulse equals momentum, where impulse is force multiplied by the time during which it acts. So we also consider the momentum here. So during the class time, so in the lecture time, we didn't consider about the momentum. All right, so here we are going to apply the Newton's second law of motion, which we will consider also the momentum. All right, so the molecule of the gases, all right, will experience a change in momentum when it collides with the container wall. Right, so you have the gases molecule and it will collide. So you have the wall. Let's say you are inside the room, okay, and then you have let's say you are okay, you the room is actually where you cook your meal, all right. So suddenly there is a gas leakage, all right. There is a gas leakage, and then the gas molecule will fill over your room, okay. So that gas molecule will spread over the the air, all right, the environment of the room, okay, and then it will hit the wall. So because your room, so it's considered like a box, all right, so it will collide with the wall, and then during the collision, an impulse is imparted by the wall, okay, to the molecule, so that is equal and opposite to the impulse imparted by the molecule to the wall. So when the molecule hit the wall, so you actually have that some forces, all right. So forces that molecule hit the wall, and then the wall give back the impulse to the molecule, so it will, okay, reflect. Okay, so the molecule will reflect. Okay, so this is actually the Newton's third law, all right, so which you haven't learned yet. Right, so the sum of impulses imparted by all of the molecules to the wall in effect the pressure. Okay, so it will give pressure. So in order to arrive at an expression for the pressure, a calculation is made of the impulse imparted to one of the walls by a single impact, followed by a calculation of how many impacts occur on that wall during time. So you will see after this experiment, you will see that whenever that molecules uh, hit the wall, okay, when it hit the wall, then you will see that there is changes in the pressure, right? So the number of impacts on the small area A of the wall, so we give us the area. So let's say your room, so we consider that as the area as A, and then in time t, okay, time t is equal to the number of molecules that reach the wall in time t. Okay. So the fundamental assumption of the kinetic theory of gases imply that, right? So we have a PV, okay, 1/3 of nmv squared RMS. Okay. So where n is the number of molecules of gas, okay, this equation derives the ideal gas law. All right. So we have PV equals 1/3 Newton meter. So we can replace that V squared RMS with the 3kT over M. And then this becomes equals to, okay, so because you can cross 3 and then you can cross M, okay, so what is left is NKT. So K is the Boltzmann constant, N is the molecule of gas. All right, and then T is the temperature. Okay, the relation between the pressure, volume, and the kinetic energy of the ideal gases is expressed as, so P is pressure, V is volume, so it's equals to 2N, all right, KE. So K is kinetic energy. Divide with 3, all right, and then that KE, so you rearrange that equation. So KE now becomes a 3 PV over 2N. All right, so the relation between the kinetic energy and the temperature of the gas is equals to KE equals to 3 over 2 KT. Okay, so actually you use PV over N. So you take PV over N over here. So PV over N, so you obtain KT. So K times the Boltzmann constant times the temperature. Okay, so for detailed introduction about this kinetic theory of the gases, so you can go through this video, okay, to learn about it. Okay, so to get a deeper understanding. All right. So now let's look at the law. Right. So we have the ideal gas law, Boyle's law, Gay-Lussec's law, and Charles' law. All right. So the ideal gas equation of state can be deduced by, for this. This is for the ideal gas. Okay. So the ideal gas equation of state can be deduced by calculating the pressure as caused by the molecular impacts on the container wall. Right, so the Boyle's law, Charles' law, and Gay-Lussec law are some laws that can be derived from the kinetic theory of gases, assuming a perfect ideal gas. So basically, the ideal gas can be derived from the Boyle's law, Gay-Lussec law, and also the Charles' law. Okay, so how about what is the Boyle's law? All right, so the Boyle's law is a relation about concerning on how the pressure of a gas tends to increase. Okay, so the pressure will keep increasing as the volume of the container decreases at a constant temperature. Let's say the temperature is constant. So let's say it's like a room. Okay, so you have a constant temperature. And also it's like um let's say inside a freezer. Okay, so inside a freezer, so that you can consider also that's a constant temperature. Okay, so but if there is fire, okay, but there is fire, there is not a constant temperature because the temperature will keep increasing. Okay, okay, so the modern statement of Boyle's law states that the absolute pressure exerted by a given mass of an ideal gas is inversely proportional to the volume it occupies if the temperature and amount of gas remain unchanged within a closed system. Okay, what it says, the Boyle's law says that the pressure, okay, by given mass of an ideal gas is inversely proportional to the volume it occupies. Okay, so the pressure will be related to the volume if the temperature and amount of gas remain unchanged within a closed system, right? So the amount of gas maintains and then the temperature also maintains. So you have P, okay, is related to V. Okay, so the equation for Boyle's law, so we have PV, all right, PV equals to K. So K is a Boltzmann constant, so which can be written as P1 V1 equals to P2 V2. So that's the Boyle's law. Okay. All right. So you see that whenever there is increment, okay, whenever there is increment, so initially you have a certain pressure, let's say 300 kilopascal, all right, and then the pressure keep increasing until 600 kilopascal, right? So what caused the change of the pressure is because of the volume. So let's say the volume before that, let's say it is 1 meter cube, but now it becomes, let's say, 3 meter cube. Okay, so that's why the pressure increases when you decrease the volume. And how about if you increase the volume? Of course, the pressure will be lowered. All right, because the relationship of the Boyle's law states that PV, okay, so initial, let's say you have the initial P, V1, and then the next should be equal to P2, V2. Okay, so if you increase the volume, of course the pressure will reduce. Okay, but if you increase the volume, but if you decrease the volume, then the temperature will increase. Okay, let's have a look at the Gay-Lussec's law. So the Gay-Lussec's law states that the pressure of a given mass of gas varies directly with the absolute temperature of the gas. Okay, when the volume is kept constant. All right. So it's different from the Boyle's law. So the Gay-Lussec's law said that, so when there is a change in the temperature, okay, when there is a change in the temperature, but now the volume is kept constant. Okay, so when the pressure of gas in a rigid container is increased, the kinetic energy of the gas increases, which causes the molecules of gas to strike the walls of container with more force, resulting in a greater pressure. So in the form of equation, so we can state that E, so the pressure equals to Boltzmann constant times temperature. So this is equals to P1 T2, all right, and P2 T1. All right, so it is like a ratio. So if you divide P1 over P2 is also equals to T1 over T2. Okay, meaning that, all right, so when the temperature is increased, okay, the pressure will also increase. So it's not like previous one where we increase the volume, the temperature will reduce. But when we increase the temperature, now the now the pressure will also increase, because P1, let's say P1 is 1, and then P2 is P1 is 1 kilopascal, and then P2 is 3 kilopascal. And then before that the temperature is 30 degree, and now the temperature will become 90 degree. Okay, so that's one example on how is the temperature relates with the pressure by using the Gay-Lussec's law. Okay, and lastly, we use also the Charles law. Okay, so the Charles law states that the volume occupied by a fixed amount of gas is directly proportional to its absolute temperature if the pressure remains constant. Okay, so now, okay, what's the difference between the other two? So the other two, we need notify that in terms of pressure. Okay, now we kept we kept the pressure constant in the Charles law. So what is changing? So what changed is the volume and also the temperature. Okay, so the absolute temperature is temperature measured by the Kelvin scale. All right. So a modern statement of Charles' law is when the pressure on a sample of dry gas is held constant, okay, the Kelvin temperature and the volume will be in the direct proportion. Okay, so in terms of equation, we have V equals to KT, all right, or V1, okay, over V2 equals to T1 over T2, meaning that when the is increased, okay, when the volume is increased, we will also have the increment in the temperature. Okay. All right. But during that time, the pressure still remain similar. Okay, so it's like okay, so it's like when you are in the small room, all right? You are in a small room and then you move now to a bigger room, okay? You will feel the bigger room will feel warmer, okay? Because what? Because the volume of the room increase. So when the volume of the room increase, then the temperature will also increase. So we need to consider that. Okay, we need to consider when you move to a room, so that room must be okay, must be closed. So the pressure remain within the room. But if it is an open door, so we don't consider that. Alright, so because that one will not be following, we will not be obeying the Charles law. Okay, so that's the three difference of the, I mean, three, three different laws that we can use to characterize the motion of the ideal gas. Okay, so let's look at this experiment. So for the first experiment, we're going to prove the Boyle's law. Okay, so you can just follow the instruction, right? So let's say I'm giving you the example here. So the Boyle's law, we can just click there. So this the similar simulation that we use on the first experiment. Okay, so basically you will have this window. All right, so first what you need to do, just follow that instruction. So you need to uh, tick on the width and also the stopwatch. So make sure your width is 10 nanometer, right? And you need to pump, right? So you need to pump. This is your pump, okay? So you need to pump the gas molecule. So roughly pump it, uh, you want to pump it around for 200 molecules. So let's say I pump it for the first time. Okay, so you can see the gas molecules. So how many gas molecules are there? How many? So you can see approximately is about 30. All right, 30. So you need to pump how many times in order to get 200? So it's about maybe around 7 times. So I already pump one. So second time, third time, okay, you can see that whenever, all right, whenever these gas molecules hit, okay, hit the wall, okay, you can see that the pressure keep increasing. Okay, okay, you can see that. Okay, let me reset that. So I just make one pump. Okay, you see that when there is no molecule hit the wall, there will be the pressure will still be zero. Okay, now, okay, now you can see that the pressure is increasing. Okay, and then increases. Okay, it increases. All right. Okay, so that's actually the relationship. When we have the molecules hitting the wall, then the pressure will increase. Okay, so I already pump once. Okay, 2 times, 3 times, 4 times, 5 times, 6 times, 7 times. Okay. All right. So you need to also click on the stopwatch, okay, because you're going to take the measurement. All right, within 5 picoseconds. Okay. So as stated in the lab manual. Okay, so later you will use it. Let's say you want to use the heat, right? So you increase the pressure, right? So this is a relationship for the next experiment. So I just give you the right. You can see that whenever, right, whenever you hit this box, right, whenever you hit that box, then you will have a energy, right? Energy of the gas will be higher because that's related with the kinetic energy of the molecule. So the molecule will move faster. And also you want to change, okay, change the width, right? Change the width of the box. You can drag, okay, you can drag, okay, or you can make it smaller. All right. So that's actually explodes, right? Because that is happen actually. It's phenomena when when the temperature is too hot, right? Let's say it is inside the room, okay? So when there is a fire, okay, when there is no way for the gas molecule to get away from uh, the room, you see that. So this is the real world phenomena that I'm saying. So you see that first the window, all right. So the glass of the window will break. Okay, so you notice that it is because the pressure inside that room is actually is very high. Okay, so it is very high. So that's why, because the kinetic energy of the gases is too high at that time, so it keep pushing the glass till it break. Okay, so let's start again. So you have the width 10, so you pump it. Okay, all right. This one you can actually open or close it. All right, so open or close. All right. So basically over here, right? So you, what constant that you want to hold? Let's say you want to investigate the Charles law, right? So for the Charles law, so you actually keep the pressure at a constant value, right? So you can actually increase the volume to see the temperature increase, or you can increase the temperature, okay, to see the, okay, you can increase the temperature to see that, okay, how it relates, okay. All right. So that's it about the experiment given, right? Okay, so it is your time to do the experiment. Okay, so let's see what else on the lab manual.
Doctor,
Yes,
I think someone is trying to enter the class.
pardon?
I think someone is trying to enter the class. Maybe someone is waiting. I don't.
Someone
I'm not
is
sure.
waiting. Yeah, I think just because on the auto admit. So
Oh,
I'm not sure. I should be in.
uh,
I know.
for the recording data, right? Can we
Yes.
use Excel as well for the recording data?
Yes, for the recorded data, you can use whatever that you want. Actually, you can just, because the recorded data is actually in terms of you increase, you keep increasing a certain parameter.
Width. Yes. Okay.
Okay. All right. Let me check back the lab manual. Okay, so basically you just need to follow what is instructed to you. Okay, so actually first one you need to record, all right? So you need to record the pressure, okay, at the time interval of 5 picosecond, right? So basically you click the pause, all right, to press the time and then process to take the measurement. Okay, so you repeat that measurement. Okay, so you actually take for 20 times because you want to see that, make sure that you, okay, because you learn about the standard deviation, so you need to find, because the value of the pressure will keep a little bit change, all right, so you need to actually take that for 20 times and then take the average measurement of that, and then you will know what is your standard deviation after that, all right, and then next you change the width of the container, all right, so you keep increasing till 15 nanometer, right, and then you also change the gas particle. So this one you choose the blue one, so next you can use the red one. Okay, so the blue one is much heavier particle compared to the red one, so red one is much more lighter. Okay, so basically after you change, you just pump it, right, so you just pump it. So let's say change, okay, you pump it, so this is now the red one. Okay, so you can see that because it is much lighter, so it will travel faster, all right. So that's the difference between the red molecules and the blue molecules. Okay.
Hmm,
Yes, you have any question?
um, so experiment and number four,
Which number?
instruction number four. How do we know the particles number are already changed 200?
As I just said, so if you pump once, how many particles are there? I just mentioned to you a few minutes ago. So one pump is about, from what I just calculated, is around 30 gas molecules. You can calculate by yourself, all right? So that's why if I pump once, it's about 30 particles, all right? Then how many times I pump? So I pump about 7 times.
The Can we press the green color button?
The green color
Because
button.
yeah, the particles there. I think we can look from there. I think so. There is. Is it the number of particles? Is it
Yeah,
exactly?
you can also use this one, all right? Let's say now you have 50 particles, right? So you can also increase that. Let's say you want to pump how many times, okay? This is one time, right? 50. Okay, so you can also use this one without manually pump that. All right. Okay, let's say we try again. Okay, you can also use that. Okay, so let's say we don't want to use the pump. All right. So if you use this pump, all right, so one pump will give you 30. All right. Okay, so it's about 200. Okay, now you have 200 molecules. You can also not to use the pump, so you can also, yeah, just press the forward play button. All right. But if you want to, yeah, play button, then it will increase slowly. All right, it will increase slowly. Okay, thanks. So yeah, so that's the two ways that you can actually um, inject the molecules into the box. All right. So you want to pump 200 molecules, so you just pump 1, 2, 3, 4. Okay, because one pump will give you 50 molecules. All right. So any other question?
Oh, yes.
So
For
what's your question?
in the instruction number 6.
Number 6.
Yeah,
Okay.
the second.
The second one, second
Uh,
experiment.
sorry, no. Experiment instruction number 6, the second sentence.
Okay, so you just actually pause the button. All right. So when you you need to stick on the width first, width and also stopwatch. So you just press play. Okay, 5 seconds. So you stop. Okay. Sorry.
On the bottom left.
This one. Sorry. This one. Okay, stop the bottom there. Not this one. All right. So you stop at the bottom here. You press pause at the bottom here. So you record what is the pressure. Okay, and then for another 5 seconds, so you record. Also, you take the pressure. Okay. Okay, so you take another pressure, and also you take another pressure. Okay, so you see that the value changes, right? So because why? Because it is not a constant value, so it changes. So you will have some error. So that's why you need to keep a repetitive of 20 measurements. All right, so you will see what is your mean. Then once you get your mean value, which is your average value, and then you will get the plus minus of your standard deviation value. This is like what you learn during the first experiment. Okay, any other question? Are you clear?
Yes.
Okay, so yeah, and later you just plot the graph. Okay, so P, the pressure. Okay, this is the average value, right? So the average value of P, okay, and versus volume. All right, so versus volume for both heavy. So this is for the blue one, and this is for the red one. Okay. All right, so basically because you change the width, right? So you change the width, so the volume will change. Okay, so initially you have 10 and you increase 11, 12, 13, 14, and 15. So you will see how the pressure change. Okay, similarly for the Gay-Lussec law. Okay, so until the number of particles is reach about 200. Okay, so in the Gay-Lussec law, you actually heat up. You heat up the the box. Alright, you heat up the box. So the temperature should change from 400, 450, 500, 550, and 600. Okay. And then similarly also, you do recording. Alright, you do recording of the value. Alright, so like the first experiment here, so you take about 20 times of the measurement. Okay, once you obtain that, so you can obtain what is your average pressure, right? And then you also need to plot, okay, what is the results for heavy particle and also the light particles. Okay, so and then you need to answer a couple of questions over here. Okay, and then for the Charles law, so you select the pressure as a constant parameter. Okay, so alright, so when the display temperature should be 300K, okay, when the display pressure should be 2366. Okay, so should be a straightforward one. Okay, and then you plot the graph, okay, similarly like the experiment 1 and 2. Okay, and then make a conclusion. Alright, so for the third one, for the fourth one, okay, so over here, you pump it for 100 times. This is for observing about the kinetic energy of the ideal gas. Okay, start the stopwatch and record the pressure in unit of kilopascal for 10 times at time intervals for 5 per second. So this is similar. So you take 10 times and then you take the average value. Okay, so but actually this one you increase the number of particle. Alright, so reset back. Okay, initially, okay, so you take the measurement. Alright, so first you inject. Okay, first you inject that. Okay, 400. Okay, so you keep constant pressure. Okay, but later you increase. So you increase the particle. So you see that. Okay. So you increase the pressure and then you will see. Alright. So that's for the number 4. And then after that, you select another one, pressure T. Okay. Meaning that the pressure and the temperature, okay, as constant parameter. So this one. Okay. Alright, so you see that. Okay, so over here, meaning that the pressure is constant, but the volume is increases, right? So over here is actually, we can count how many, if you are interested to know more, so you can click on the collision counter, so you can count at that time, okay, let's say 5 picosecond, how many times the wall is hit, okay, by the molecules. Of course, you see, if I increase the volume, okay, let's say within 5 picosecond, so it hits 139 times. If you increase the volume, it will be larger or smaller. it will be smaller, right? Because the molecules now have more spaces, so the motion between the molecules will be much higher, all right? Because the motion will be much higher because the molecule have more spaces to move around. All right, so I think that should be a clear one. All right, so you have until that for lab. 4 experiments need to be done for your lab report. Okay. All right, so any other question before we stop? So you will need to do that. All right, so the lab report will be due in the next 2 weeks. All right, so because you have, so for the next week, the tutorial will be due. All right, and then for another week, the lab report will due. Okay. Any other question? Right, if there is no question, then let's turn on your camera. So we stop here. All right, so come on everyone. So turn on your camera. Okay, all right, so let's count from 10. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Cheers. All right, one more shot. Okay, another style. Munira, is a very nice view over there. So enjoying the morning sun. Okay, so I see you again on Thursday. All right. So have a nice day, everyone. So enjoy the rest of the day. Okay, and happy fasting for those who are fasting. All right, and then so I see you on Thursday. All right, all the best. Say, have a nice day. All right, okay, see you. Okay, bye bye.
Thank you, Doctor.
Thank you,
Thank
Doctor.
you,
Welcome.
Doctor.
Thank you, Doctor.
Thank you,
Happy
Doctor.
fasting.
Thank you, Doctor.
Thank you, Doctor.
Okay, welcome.